Okay, so this is, I believe, lecture number 6, and we're going to pick up right where we finished in the previous lecture. So, in the previous lecture, we have discussed 3 major different categories of measures that we can calculate for a numerical data set. They include measures of central location, most popular is mean, second choice, most popular is median, and the least popular is the mode. And we discussed second big group, measures of variability. They include range, variance, square root from variance is called standard deviation. Then there is interquartile range and also coefficient of variation, CV. And finally we discussed measures of relative standing, called percentiles. There are standard percentiles, they're called quartiles, but you can calculate different percentiles, and that's what we're going to do actually in this lecture. Okay, so practical example, time in the restaurant. So let's read it first. For many restaurants, the amount of time customers spend over coffee and dessert negatively affect profits. So in other words, people come in, they order something cheap, relatively inexpensive, coffee, piece of cheesecake or something like that, and they sit there for 40 minutes just talking, right? So to get more insight into how much time people tend to spend in the restaurant, here is what the owners did. They selected 200 groups of people. So it can be a single person coming in, or 2 people, 3 people, whatever. And for each of these groups, they recorded how much time, in terms of minutes, the group spent in the restaurant. So the data are recorded in the file restaurants.csv. So let's go back to our Scholar, and here is our Scholar. It's all in the data sets, right? So click on the data sets. Here is the file restaurant.csv. So let's download the file, and again, just like what we always do, at least for the PC users, right? I go to the downloads folder, and in the downloads folder I'm going to cut the file and bring it to the data right here. Okay, so here's my data set, and here in the preview window I can actually see that it's only one single column, right? Well, don't worry about that. In the next example we're going to be dealing with 2 different columns of the numerical data. Okay, and the column is titled time. So these are all different times in minutes that groups of people, 200 of them, spent in the restaurant. Okay, beautiful. So I'm going to fire up my RStudio. There you go. And since this is another chapter, I'm going to create a new R script. And that goes, I guess, without saying that if you guys watching this lecture, you need to follow what I'm doing on the screen with your own RStudio on your machine. So just follow what I'm doing. So here I'm going to read CSV file restaurant CSV. Okay, beautiful. So I'm gonna have to call my data frame somehow, right? Because the data that I'm reading again comes into my internal variable, which is a data frame, right? So how do I call it? Well, restaurant data. How about that? And that is done by the function read CSV. We did it several times already, and as we go through the semester, we'll do it 50 billion more times, so you will get used to that pretty quickly. It's located on the drive C in the folder data and file called restaurant, but I have to remember to include the extension .csv, right? Otherwise it will curse at me. So I'm gonna run this line. There it is. So just like before, I'm gonna say let's explore structure of the data. Okay, so str of my data, which is called restaurant data, right there. Kaboom. So it says that I have 200 observations, so 200 people or groups of people, and one variable only, one column in my data, and it's called time, and it's numerical, not just numerical, it's integer, there are no decimals. And here are some values from the top of the file. Okay, beautiful. Alright, now let's go back to the PowerPoint and see what is that we want to do with this PowerPoint. Okay, construct the histogram. Is the histogram symmetrical or skewed? If it is skewed, then is it right skewed or left skewed? Calculate for the data, because it's numerical data, so we can calculate all kinds of burritos about that. Calculate the mean and the median. What is the range for the data? So these are the measures of central location, right? Then we're moving on to the measures of variability. Calculate the range and the standard deviation. Then after that, find the 25th percentile and 46th percentile. So these are the measures of relative standing, right? And we're going to interpret them as well. And then find such time spent in the restaurant by customers that 60% of the customers stay longer than that time. Okay, so that's also actually about finding the percentile, but which specifically. Alright, we're going to find out. And finally, are there any outliers? Okay, so let's go with this plan. So first things first, let's do the histogram, right? Well, from 2 lectures ago, you remember that to plot the histogram, I have to use the function HIST, right? So plot data histogram. So HIST, and I have to tell which data to plot, right? So well, there is only one column, so how do I call up on this column? Well, here's what I need to do. I need to say my data name, which is restaurant data, and after that, to call specific column, I have to say $, and pick the one that I want to explore, right? Okay, so and that technically is enough. So I'm gonna run this line, and there it is. Okay, here's my histogram. But just like we did before, let's make it more cultured, more civilized, right? So for example, I want to replace the main title, and frequency is okay, I guess. That one, also the X label. So main title, quote unquote, I'm gonna say distribution of time in restaurant. There you go. And the X lab, right? The label for the horizontal axis is quote unquote, what should I say? Time in minutes, right? Time, comma, minutes. Alright. Yeah, that's good enough. So let me rerun this line, and here is my slightly better looking histogram. So what can I say from this histogram? Well, number one is the model class, right? Remember, the model class is the tallest bar, right? That's the most frequently encountered set of times. The model times are between 25 to 30, right, minutes. So therefore, what can I say? Typical time, the most frequent time that customers spend in my restaurants are between 25 to 30 minutes, right? That's how I interpret the mode. Non-symmetrical, pretty obvious, right? Where is it skewed? Well, again, the skew of the distribution is where the long tail points. So the long tail goes to the right, so it's a right or positively skewed histogram. Simple as that. Okay, so we're done with part number one. Part number two, calculate data mean and the median. Guess what? So simple, it's scary. You can probably guess how it's done, right? So I'm gonna say here, calculate measures of central location, because mean and median, as we discussed, are measures of central location. Mean is calculated by, surprise, surprise, function called mean. And as you can guess, all I have to do is send this function just a set of numbers, set of values. What are these values? Well, data set is called restaurant data, then I have to say $. Here's the column that I want you to calculate the mean for, right? Bam. Okay, so the average time that people spend in the restaurant is 29.93. So let's call it 30 minutes, right? On average, people spend 30 minutes in the restaurant. Okay, and median is completely identical to the mean. The only difference is that the function that we're going to call is called median. Alright, and the same thing, I have to send the function, the argument, which is a vector of the numerical values. Okay, so dataset restaurant underscore data, $, column time, and that's my vector of the values. So I'm gonna run this one, and there you go. Median time is 28.5. Okay, so it's that simple. I'm not going to even spend too much time on that because it's so it's almost Excel, right? You can do pretty much the same with Excel, except the mean in Excel you calculate using the function average, right? Here the function is called mean. Everything else is the same, identical. Okay, so we're done with the second part of this program. What is the range and the standard deviation? So both range and standard deviation are the measures of what? They are the measures of variability or inconsistency. So let me leave a comment here. Calculate. Okay, I'm going to fix that one. Calculate measures of variability. Okay. So range. Well, now let's just go with it. Okay, range. No, not this one. Range. Of it's all the same. Of set of numerical values. Okay, so restaurant data, $, column time. Bam. So what it gives me, you can see, I'm gonna give it a couple of entries so that it comes to the field of view, so to speak, right? Here's my range. Obviously 21 is the minimum and 55 is the maximum, right? So this is the smallest and the highest number. Just like in Excel, actually I can calculate mean and max. So let me show you mean of, and you know what, let me just copy paste restaurant data $time. I'm going to use it again and again and again, so I'm going to just copy that in the clipboard and just paste it whenever I need that. So minimum of the data can be calculated using mean function. There it is, 21. Maximum, drum roll, is going to be function max. Same thing, right? Data, restaurant data, column time. There you go. That's your 55. Okay. So we're done with the range, right? Range is between 21 to 55. Okay, standard deviation. Now, standard deviation, let me actually calculate it in a couple of different ways, and you will see that they are identical. Standard deviation, if you remember that from our previous lecture, is just simply square root from the variance, right? So I can go ahead and calculate the variance. Variance is calculated using VAR function. Okay, so I'm going to go ahead and say variance of this data, and there it is. Okay, actually, you know what? I'm going to leave a comment right here. Because there var is what is var, right? Calculate data variance. Okay, and you know what? I'm going to assign that to the variable, which I'm going to call sample variance, because it is a sample, right? I have 200 people out of how many? Thousands and thousands, right? So it is a sample. So sample variance is just VAR variance of the restaurant data column time, and then standard sample underscore standard underscore deviation, okay, is square root from sample variance. And guess what? Square root in R is done using the same function as what we use in Excel. That is SQRT, square root from the variance, right? So I'm gonna copy. No, I'm going to just type it sample variance. Okay, sample standard deviation is the square root from sample variance. We're following precise, exact definition from statistics, nothing else. Whoops, I misspelled something, didn't I? Okay, so it doesn't like sample variance. Why? I tried to copy paste it. Oh, I didn't run this line. Okay, I think I get it. Right? So see, the reason why I didn't misspell anything actually. So it's the same exact thing, but the reason why I have an error here is you need to run the line for this variable to exist. You see that? There is no such variable right now. Okay, so I have to run line number 1 first. It will calculate the sample variance. Right? I mean, I calculated that before. Right? I ran the function. Just I didn't assign it to the variable. Right? So this variable didn't exist. Now it does exist. It's right here. Okay. So and now I can use it in the second step, taking the square root from this variable. Okay. So, and that's actually one of the mistakes that I oftentimes, not oftentimes, but once in a while see on the exam. Okay, people show me exactly that. They're showing me, okay, it says an error, the object such and such not found, and I'm telling them that, you know, when you wrote the line of code, it's not enough. You have to run the line of code, and then only after that your new object will start, you know, existing, so to speak. It will be present in the memory. So now I have sample variance. I can take square root out of that, and then let me show it. So I'm going to say sample standard deviation, and it's just simply 5.99. It's the square root from 35.95. That's it. Okay. So standard deviation is 5.99. Let's call it 6, and the units of measure are minutes. Right? Remember, in the previous lecture we had a big fat discussion about variance has units of measure, your original unit squared. So if you're measuring dollars, it's going to be dollars squared. If you're measuring temperature, it's going to be degrees Fahrenheit squared. But when you take the square root and get the standard deviation, you're back to your usual normal original units of measure. So in this case, we're measuring time in minutes. Therefore, the standard deviation is 6 minutes. Okay. Now let me show you another way. So here we kind of did it in 2 steps, right? Step 1, calculate the variance, and step 2, take the square root. Well, obviously there is a shorter way, right? And you can do that using SD, right? So here I'm gonna say calculate standard deviation using function SD, and SD obviously stands for standard deviation, right? So SD of my restaurant data column time, and when I run it, not surprisingly, it's exactly same number, right? So I can calculate it as the square root from the variance, or I can straight calculate that using the SD function. The result is identical and the same. Okay. All right. Moving right along. Calculate the 25th percentile and 46th percentile. Let me show you a couple of tricks. Well, not tricks, but a couple of ways, right? So, as you understand, we're now done with measures of variance, right? Measures of variability, not variance, measures of variability. Now we're moving to third big part, calculate measures of relative standing. Okay. A very useful function that I'm about to show you is very simple to use. Okay, it's called summary. So I can go ahead and calculate summary of my column of data. Okay, restaurant data column time. So if I'm using the function summary and I run that, you can see that it gives me 5 numbers, right? No, more like 6 from what I can see. Yeah, it adds the mean. Okay, so it gives me so-called 5 number summary plus extra one. Okay, so if I forget about the mean, all right, if I forget about the mean, then I'm getting something that's called 5 number summary. Very popular measure actually. So remember when we just started this topic, numerical measures, numerical descriptive measures, I told you, I believe, right off the bat that this chapter is going to be about how we can take a whole bunch of numerical data. It can be thousands and thousands of numbers, okay, and characterize it by a handful of just summaries. So condense essentially many thousands of observations potentially into just 1, 2, 3, maybe 5, maybe a little bit more, 7 of them, 7 different numerical measures. Okay, so standard term pretty much in statistics, and you can Google it. It's called 5-number summary. So 5-number summary for a numerical data set is this. Number 1 is what's the minimum. Number 2 is what's your first quartile. Number 3 is what's your second quartile, otherwise known as median. Number 4 is your third quartile, and number 5 is your maximum. So mean, Q1, Q2, Q3, and max are called 5-number summary. Or you can see that summary function actually gives me the 5-number summary plus also the mean. Okay, so 25th percentile, right? That was my original question. Find the 25th percentile. It's my Q1, first quartile, and there it is. It's 26, right? How do I interpret that? 25% of people spend less than 26 minutes in the restaurant, and therefore 75% of people spend more than 26 minutes in this restaurant, right? That's my interpretation of first quartile. Now, the next question in my PowerPoint slides was calculate the 46th percentile, right? And 46 is not one of the big 3 quartiles, Q1, Q2, and Q3. So this is custom percentile. So if I want to find a non-standard percentile, then I have to use the function that is called quantile. So go ahead and start typing quant, and it will show quantile. Okay, and the description there says generic function. Quantile produces sample quantiles corresponding to given probability. So in other words, I can specify what kind of quantile I want, and it'll calculate it for me. So quantile, a couple of things that I have to send to the function. First of all, obviously the data set itself, right? You want to find quantile of what? Well, here is my set of times. So use that as my data, and after that I have to specify what is my what's the percentile that I'm looking for. Well, in my case, it's 46th percentile, which means that the probability is 0.46, right? I have to convert the percentage into the fraction between 0 and 1. Okay, so when I run this line, it tells me that the 46th percentile is 28. So again, what's my interpretation of that? 46% of people spend less than 28 minutes in the restaurant, and therefore 54%, 100 minus 46, right? 54% of people spend more than 28 minutes in the restaurant. Okay? By the way, useful exercise, okay? What do you think will happen if I'm going to calculate quantile for the same data, but the probability is 0? So this is where the popular YouTube videos tell you, okay, you can pause the video now, find the answer yourself, and when you're ready, click play again, right? So I'm going to pause for 5 seconds and tell you the answer. So the answer is, I'm looking to find here the 0th percentile, right? That means that I'm looking for the numbers such that 0% or nothing in my data set is smaller than the number, but 100% is above that number. So it should give me the minimum, right? And the minimum is 21. Let's see if that's true. There you go, 21. Okay, so in the data set, 0th percentile is your minimum. Let's go to another extreme. Quantile, same data, but now instead of 0, I'm going to use 1. Which corresponds to 100%, right? So the answer again here is going to be what? Well, I'm looking to find the 100th percentile, right? That means that 100% of the data is below that number and 0% of the data is above. So it's going to give me the maximum. The maximum is 55. Well, let's see if that's true. Yes, indeed it's true. So 0th percentile is the minimum and the 100th percentile is the maximum. Okay? Alright, moving right along. Now that one might be tricky, a little bit. So let's see. Find such time spent in the restaurant by the customer that 60% of customers stay longer than that. Well, here is my line of thinking. If 60% of customers stay longer than this t that we're looking for, that means that 40% of the customers stay shorter than that time, okay? So 40% of my data should be below that t that I'm looking for. And therefore, by definition, what I'm looking for is really 40th percentile, right? So let's find out. Again, it's custom percentile, right? So let me put actually a couple of comments here. So 0th percentile is minimum, right? And here I'm gonna say pound sign comment, 100th percentile is maximum. Oops, maximum. All right. Very cool. So now I'm gonna find Quantile, right? Function Quantile, and here's my data set. I'm just copying Control V because I'm just pasting that Control V, right? Because I copied that before, so now I'm just copying that down. 40th percentile is what I'm looking for, so 0.4, right? And when I run that line, it's 27. So 40% of customers spend less than 27 minutes in the restaurant, and therefore 60% of customers, 100 minus 40, spend more than 27 minutes in this restaurant. So that answers this next question, right? Find time such that 60% of customers stay longer than that. That's 27 minutes. Are there any outliers? Well, let's see. For the outliers, we need to find, we need to plot box and whiskers plot, right? And that, ladies and gentlemen, is our plot number 3. In the previous lectures, about 2 or 3 lectures ago, we learned how to plot a box plot. Not box plot, sorry, box plot we're going to plot right now. Bar plot, right, for the categorical data, and also histogram for the numerical data. So now I'm going to plot a box and whiskers. Oops, whiskers plot. Okay. So, and that is done by the function box plot. So as I start typing box, I can see that the function is right there. It's one of the standard functions included with R by default. So box plot, well, theoretically, all I need really is just send it to data set. So again, paste, Control V, restaurant data, $, column time. And when I run this one, here's my box plot. But it looks a little ugly, right? So I guess default orientation for the box plot is vertical. Let's see if I can put it on the side, horizontal, right? So my guess, we did it before, right? We did it with bar plot. Didn't quite work out with histogram if I remember correctly, but let's see. So if I say horizontal, right? Yeah, so box plot can actually turn on the side. So there is a parameter for the function box plot called horizontal. And I guess it's also true or false, right? That's what we did for the bar chart before. So if the parameter is true, and all caps, right, TRUE, then it's going to be horizontally oriented. So let's try that, and there you go. So all these points right here, okay, my guess is that it's above 41. Everything that's above 41 minutes is an outlier. So according to this data, these numbers, right, I don't even know what they are, quite frankly, but anything above 41 minutes is unusually long. So and it spans all the way up to 55 minutes, right? So this is not normal to spend longer than 41 minutes in the restaurant. That's what this graph is telling you. So these people, or groups of people, right, that spend longer than 41 minutes, they spend an unusually long time in the restaurant, okay? And actually one other thing that I wanted to emphasize is from the box and whiskers plot, you can pretty much see the same pattern about your data distribution as you can see from your histogram. So let me go ahead and rerun the histogram, okay? So right here, right? I'm going to show you the histogram. We discussed that histogram is right skewed, right? So there is a bunch of data right up front for the lower values of the times, and then as times go into the larger and larger values, we have long tail going in the right direction. Can we see the same pattern from the box and whiskers plot? Yeah, we kind of can, right? Because here you don't have any outliers on the left side, right? And this whisker is relatively short. So therefore this is first half of your data. You can see that, right? 50% of your data is to the left from the median, and this is the median right here in the middle, okay, of the box. And you can see that it has much longer data distribution to the right from the median, and you can see that this 25% of the data above the median is longer, right, than this 25% below the median. This whisker is longer, and we have some outliers. So you can kind of glance at the box plot, and box plot will tell you if the distribution is symmetrical or not. So if the box is symmetrical, right, if this median is right in the middle of the box, and your whiskers have the same length, then you're dealing with symmetrical distribution pretty much. Okay, but of course histogram is much more detailed, right? So this is called a 5-point summary for a reason, right? You have minimum, maximum, Q1, Q2, and Q3, right? So you don't have any visibility into, you know, how the data are distributed pretty much anywhere, right? As compared to histogram, where you can see pretty much where the peaks and valleys are, how many peaks you have, etc. Okay. All right. So and that, I believe, concludes this problem, right? Are there any outliers? Yes. Anything higher than 41 minutes is an outlier. And everything that we did, I pretty much put in the PowerPoint slides. PowerPoint slides are uploaded on the Scholar. So when we're done with this set of slides, I'm going to also post, just like I usually do, right after the PowerPoint slide, the R script that we just created. But before we go, okay, before we finish this lecture, let's discuss yet another problem. It's about coefficient of variation, as you can see, right? So here is a problem. Operations manager of a truck shipping company, okay, something like, I don't know, FedEx Ground, okay, or UPS. So the company that ships boxes, delivers the boxes, is trying to decide, trying to find out which is more uncertain in package shipments. Is it the package weight or is it the package volume? When we say uncertain, that means it's actually dealing with variability, okay? Uncertainty in statistics is another term for variability, simple as that, okay? The more variability you have in the data, the more uncertainty you have in the data, okay? So, in other words, this question really boils down to which is more variable, the package weight or the package volume. In other words, how big is the package, right? How bulky it is versus how heavy it is. Which one is more uncertain? Okay, so he decides to take a sample of 200 packages and measure their weights and volumes. And based on this data, which factor contributes more uncertainty, weight or volume? So use file weight versus volume. Okay, so, and this is the last thing that we're going to do in this exercise, in this lecture, so let's get right down to it. In my data sets, right, here's my Scholar. In the folder data sets, I have the file weight versus volume, CSV, just like always. I'm going to download this file. I'm going to go to the downloads folder. Here it is. So cut, bring it over to the folder data and paste. Well, apparently I have it here already. So let me go ahead and replace that. Okay, so now, all right, I'm going to pretend I didn't see anything. So, but you can guess that I have 2 columns now, right, in my data. So here's my preview. I have my weights and I have volumes. Okay, so weights are measured, I don't know, in terms of ounces, for example, okay, and volumes are measured in terms of cubic, probably not feet, there's just large, right? Cubic inches, let's say, whatever it is, okay? Alright, so let's go back to our studio, okay? So here I'm going to just to visually separate problem number 1 from this problem number 2. I'm going to put a bunch of dollar signs, pound signs. Okay, so analysis. So I'm going to say analysis of packages, weights and volumes. Alright, so first things first, of course, I have to read in the data, right? Nothing happens before I have data sitting in the memory. So packages, data, okay? And I'm gonna say use the function read CSV just like I always do, and the exact location is C drive data. God, what's the name of this thing? Weight underscore vs underscore volume.csv. Okay, so here I'm using PC, that's why I write C data. If you're using Macintosh, then probably you have to start with tilde, right? We discussed it before. That's just FYI. Okay, so I'm gonna run this line. Yep, it doesn't curse at me, that means that the data is in. So let's take a look at the data structure, right? Look at data structure. Okay, so str, right, of my data, which is called package underscore data. There it is, package data, packages data. Okay, and now it's different a little bit, right? We kind of, so far we were dealing with data sets that had one variable, right? One column, that means. Here I have two variables now. So there are 200 packages, just like what problem promised. Okay, and there are two columns, two variables. Weights, it's a numerical variable, right? You can see that it's not int anymore, not an integer, because guess what? We have decimals. And the second column is called volumes, also a number because we have decimals, right? Not int, but num number. Okay, well, how do we measure the variability? What's more uncertain? Well, the thing that has more variability in it. How do we measure variability? Obviously standard deviations, right? First thing that comes to mind. The most frequently used measure of variability is the standard deviation. So I'm going to call it SD. Okay, so calculate. Let's deal with weights first. Weights, SD, standard deviation. So SD underscore weights. Okay, so I'm gonna save it in the memory, right? Under a certain name, and the name is SD underscore weights. So I use the function SD, standard deviation, and obviously I have to point to the right column in my data. Now I have two columns, right? Unlike what I had before. So packages data, okay, packages data right there, and dollar sign, and I have to pick weights. Okay, bam. And I'm gonna do the same exact thing for you know what, here calculates weights and volumes SD. I don't want to put another comment line right here. Alright, so I'm gonna call it SD underscore volumes. Okay, and that would be SD, same thing, packages data, dollar sign, but this time around I'm going to pick another column, which is volumes, right? And I run this line. Now let me just see what they are. SD, weights, so I'm going to run this line, and also SD underscore volumes, I'm going to run this line. Okay, so what do we have? Well, we have for the weights, the standard deviation is 4.03, and for the volumes of the packages, the standard deviation is 2.27. So what did we discuss? The higher standard deviation, the more variability you have. So that means that weights are more variable, they're more uncertain, therefore they contribute more uncertainty into the process of filling up trucks with packages, right? End of story, case closed. Yeah, but weights are measured in terms of ounces or pounds, whatever that is, right? And volumes are measured in terms of cubic inches or cubic feet, whatever is used, right? So really what I'm saying is 4.03 ounces is greater than 2.27 cubic inches. So I'm comparing apples and oranges, right? I cannot just look at the numbers themselves because the measures are different, okay? Can't compare ounces or pounds versus cubic inches or cubic feet, right? They have to be in comparable units. And how do we make them into comparable units? We're using coefficient of variation, CV. And the formula for the CV, if you remember, is standard deviation divided by the mean. So here I'm going to calculate also the means, right? So according to my, bottom line here, the moral of the story is, if I use standard deviations and kind of forget about the units, right, then weights are more variable because 4.03 is higher than 2.27. Clear case. Alright, but now let me go ahead and calculate weights and volumes means. Okay, mean. Alright, so, and I'm going to give them the same name, right? Mean weight. And that is done, if you remember, by the function mean, right? And that would be mean of what? Packages data, right there, $, weights, right? Mean weights is data packages data, column weights. Bam. And I'm going to do the same thing, mean underscore volume. And for that, I'm going to use the same function mean, but the column now from the data packages data, right there, $, I'm using volumes, right? Okay, cool. Now a little, just for the heck of it, let's see. Mean underscore weight is what? The average weight of the package is 26.02, I don't know, ounces, pounds. Probably ounces. That's too heavy for the package, right? And the mean underscore volume is 8.817, but that is cubic inches, for example, right? If that's what reported in the file. Okay, and now I'm going to calculate, because I have to compare unitless measures of variability, and that would be CV, right? Compute, calculate. CV for weights and volumes. Okay, so CV underscore weights is simply SD for the weights, right, divided by the mean underscore weight. SD weights by the mean weight. Okay, and similarly I'm going to calculate CD. I'm going to call it CD volumes, and that is going to be equal to SD for the volumes divided by mean underscore volume, right? Standard deviation divided by the mean. Okay, volume. All right, and now let's just print them out. CV for the weights, print that out, and CV for the volumes. Bam. Okay, so when I was looking just at the standard deviations, weights were more variable, right? Because the standard deviation was higher for the weights. Now that I'm looking at the CVs, units without a measure, right? Just a number, what do I see? CV for the volumes is 0.25 and CV for the weights is 0.15. So based on these two numbers, the coefficient of variation for the volumes is actually higher, right? And therefore, I have to reverse my previous diagnosis and say that volumes are more variable than weights. So, contrary to what I was, seeing from the standard deviations, in actuality, it looks like volumes are more variable. Okay, they contribute more to the uncertainty. Okay, and that concludes this lecture. We're actually almost at 50-minute mark right there. So we're done with this chapter about the numerical descriptive measures. Again, they apply for the most part to the numerical data sets. So if your data set is nominal or ordinal, none of that stuff that we did, almost none of the stuff that we did today is applicable. Okay, the only thing that you can calculate is for ordinal data, you can calculate the mode, the most popular category, and also the median, because ordinal data can be ordered from lowest to highest values. And for the nominal data, you can calculate only the mode, and that's it, nothing else. Okay, so I'm going to save that R script, and I'm going to post that in the lecture notes right after the PowerPoint about the numerical descriptive measures.